Welcome to Mr. Carlson's lab. Often, substituting an electronic component in a circuit is very needed, just because the original component has become unavailable now, and there are other reasons as well. Today, I'm going to share some electronic component knowledge with you. These tips and these tricks will help you choose a modern component for your device that will work equally as well or better than the original component. So let's get started. Let's talk about power supply filter capacitors. So this has been a heavily asked question throughout this Grand Receiver Restoration series. Up here is the original capacitor, and that's an oil-filled type capacitor at the top, and that's rated at 4 microfarad for each section in there. And I've replaced those with a poly capacitor down here that's rated at 4.7 microfarad. Now, whenever you're replacing a capacitor in a power supply like this, that extra 0.7 microfarad, almost 1 more microfarad, is really not that incredibly important. The only time that capacitance gets very important is in oscillator circuits and any type of a timing circuit. When you're dealing with a power supply or something like that, especially when you're dealing with the bulk supply, basically a very crude filtering supply, that little added extra capacitance isn't going to hurt at all. Now, this doesn't count in every single application, but in the majority, that's really the way it is. Now, of course, the second question is, Paul, why did you replace them with a poly style capacitor? Why didn't you go with just an electrolytic capacitor? Okay, so here's something that is very confusing, and this here will immediately go, wow, okay, that makes a lot of sense to many of you here. So the radio receiver is on right now, which means that there's B+ flowing through the chassis. And many of you are thinking, those are poly caps, and they're quite a bit more expensive than just a standard electrolytic. So why didn't I just use electrolytic capacitors in here? Well, here's one of the big tricks, all right? So I'll just move around here. So what I'll do is I'll put the probe on the filter reactor here, right pretty much where it comes out of the vacuum tube, right out of the rectifier. So that's the voltage that's right at that. So that's pretty much right at the rectifier tube, all right? 307 volts. All right, so that's what that is there. Now you're thinking, wow, 307 volts, that's probably okay to, use a 450 volt capacitor, right? How much overshoot could there really be? Well, here's the trick, and you always have to look for this, because if you don't, it's going to catch you one day. So what I'm going to do is I'm going to let this cool down, and I'm going to attach that probe up to here, and I'll turn it on once it's cold, and we'll see what the voltage starts out as. All right, the radio receiver is cooled off, so we are going to get basically the maximum amount of overshoot even in transmit mode here. So transmit mode on the radio receiver basically cuts the B+ to the rest of the receiver, so there is no load on the supply, and then of course the supply will usually go quite high up. So I have this tied into circuit already with just an alligator clip, so I can turn the thing on and be by the switch here, and you can watch the meter and see where that voltage goes. So here we go. $457 volts in transmit mode. That's pretty high up. So that exceeds a 450 volt capacitor. Now, of course, if I go to the receive mode, drops down to 309 now because the supply is loaded. And this is just nice enough to give us the option of reducing the radio's load by opening the B+ line, but you get the same kind of effect in a regular radio receiver when the tubes aren't warmed up, because when the tubes aren't warmed up, there's no load being pulled, so the voltage will skyrocket like that. This has a switch which allows us just to do this. So I'll snap it back into the transmit mode, and you can see every now and then, there was 467 there for a moment. 472, did you see that? So now this is just as quickly as this meter right now is set up there. The meter isn't really responding to a very quick event right now, right? It's just going as quick as the meter can read this. I was using the oscilloscope here, and I was basically triggering on it, we could get an absolute peak here, but it's way up there. So 460 that time. 468. Yeah, so you can see we get some pretty high excursions, and just with this sitting in the transmit mode, it's above a 450 volt cap. It's 454 volts. So if you were to put this in standby or to transmit, the regular electrolytic filter cap would be sitting there. You might be saying, well, why don't you just buy a 500 volt capacitor? Well, you got to remember there's still resistors and things in here, and you know, of course, the supply voltage itself, the supply to this radio receiver is lower than a standard, you know, what's at a standard wall outlet. So even at 500 volts, I still wouldn't feel comfortable with a 500 volt cap in here. There just isn't enough of a safety zone. So that's why I went with these capacitors right here. Let's grab one, make sure I've got it the right side up. So this is the capacitors that have, or these are the capacitors that have been installed in the radio receiver there. So 4.7 microfarad, 630 volts DC. That's those three capacitors right there. So there's a lot of safety zone there, and since they're a poly style capacitor, they'll outlast any electrolytic. So they'll just keep going and going and going. In fact, those are probably the last filter capacitors that this receiver will ever see. At least I'm pretty positive of that anyways. So there you have it. So transmit mode or standby, and then in receive, a huge difference. Now again, keep in mind if you're working on a Hammerland or a Collins or anything else with a vacuum tube power supply, when the tubes are first turned on, all the filaments are cold, so none of them are drawing current. They all have to warm up, and then as the tubes warm up, it starts to pull the supply down, and then that's why you get this effect right here. There's such a huge difference between technically the open circuit and the loaded circuit, which you see right here. I should also mention regarding those filter capacitors, this is also valid for guitar amplifiers, test equipment, televisions, power supplies, all sorts of things. A lot of the times there is quite a difference between the loaded scenario and the non-loaded scenario. A really good example of that would be if you have a guitar amplifier and you click the guitar amplifier into standby. In some circuit designs, that causes the power supply voltage to go quite high because it removes load. Again, it depends on the design of the guitar amplifier. Not all are like that. Some of them open up the center tap on the B+ winding, and there's all sorts of different designs out there. So always something to keep in mind. It's always something that should be researched before making a final decision on capacitors. Of course, it goes much deeper than that too if you want to get into ripple current and things like that, but that's a really big topic. I'll go into that here in the future. Now, another thing that we've discussed in this radio receiver, we found, I should say, is that most of all the bypass capacitors in this radio receiver are noisy, and they've used mica capacitors in here. Now, I've had the question, Paul, are these paper? I've mentioned this before, and then of course I said in the previous video to the last, these are not paper, they are mica, and I explained that. So these are not paper. They are technically, the package for a mica is a pretty large value. 4,700 picofarad is pretty big, but yeah, still not big enough to need to be paper, right? So being the 40s and 4,700 picofarad capacitors, that is about the right size. In fact, the other radio receiver that I have, I believe it's a GR17, which I'm going to be using for parts for this one here, has a different style of mica capacitor in there, and we'll also compare those here in the future. Now, another commonly asked question is since these are all micas, you can see they're using mica capacitors for bypass capacitors in there. Do I need to replace these bypass capacitors in the RF, an oscillator and mixer section with mica capacitors to keep things stable? Well, no, you don't. Not as bypass capacitors. Again, anything that's in an oscillator circuit or anything that is used for timing will need to remain a mica capacitor or an NP0 style capacitor. But since these are just bypass capacitors, these can be replaced, and their value can also be increased as well. Again, way back when, in this particular radio receiver and many others, the reason that they're using these mica capacitors is because they're extremely dependable. They're much more dependable than a paper and foil style capacitor. So 4,700 is a very, very large capacitor. Pretty much, I would say, close to the largest style of capacitor that would I guess you could say, fit into this design. So what they did is they used 4700 picofarad capacitors as the bypass caps. If they wanted to, say, go to a 0.01 microfarad, which would have been a much better choice for this, is, you know, of course you would have double the size. It would be double the thickness of this capacitor. You know, 4700 and 4700 and just a little bit is going to be, you know, very close to 0.01 microfarad. So you can pretty much picture that as double the thickness. The same thing they did in the audio section. If you watch the earlier episodes where they put two 4700s in parallel in the audio, you know, you have this really big, thick sandwich of mica capacitors. So they went with a 4700. Now, when I go about replacing these mica capacitors, since they are bypass capacitors and they're basically just on the screen line, and some of them are on the B+ line, the main B+ line, they can be replaced with a standard poly capacitor. If I was to go and try to find, say, 4700 picofarad mica replacement capacitors, that would be extremely expensive, completely unneeded. I would be going with a lower value than I could actually install in here. I can improve the design by just installing, you know, a 0.01 microfarad poly capacitor. Again, the poly capacitor in a bypass circuit in here is not going to incur any type of drift into the circuit whatsoever. It's basically just keeping the screen line and the B+ line noise free, and it's stopping stages from seeing one another as well. All right, so this is an AVC capacitor down here. It's on the AVC line. This thing will be replaced with a 4700 picofarad capacitor because I don't want to change the AVC time constant at all. So that will be replaced with a standard cap. And these, just the standard type of bypass cap, will be replaced all with 0.01 microfarad polys. So that is this cap here, this one here, this one here, this one here. There's one hiding in behind here, and there's some down on the bottom, and there's one in there. Now you'll see more of these mica capacitors. These are not 4700 picofarad capacitors, and they are not bypass capacitors. So they're, again, in circuitry that hasn't been used as bypassing, and I will test those to make sure that they are silent. You do not want to change any mica capacitor that is in an oscillator circuit in an old radio like this unless it's absolutely necessary, because you're going to mess with the dial tracking. Again, you're dealing with an analog device, basically two analog devices. You're dealing with an analog type oscillator, and you're dealing with the dial on the actual faceplate. So you have to align the oscillator and make it track with what the dial face says. All right, you have this big capacitor in here that moves on the top side of the chassis as you're spinning that dial. The plates are meshing, or they're being opened from each other. So when you change any type of a capacitor like this one in here, these ceramics are extremely stable. All right, these here almost never need to be replaced in any type of application, and usually they have some pretty stringent temperature coefficients. It's the reason that they use these in these particular circuits here. So if the circuit is going to drift one way, sometimes the capacitor will drift in the opposite direction, and you get this evening effect. All right, a lot of thought in the engineering department at RCA went into this, so you don't want to be ever fooling with these. If you were to replace these capacitors with a ceramic, just a standard ceramic capacitor, and replace these micas here with say a standard ceramic that isn't an NP0 or C0G rated cap, this oscillator would be the most unstable thing in the world. You would have to have a steering wheel on the front of this thing, and you'd be moving it back and forth trying to keep it on frequency with just the most slight temperature variation. So very, very important to keep those capacitors the same. Again, bypass capacitors that are on B+ lines are not dealing with anything that's going to incur drift in the oscillator circuit. It's just, again, keeping the screen grid quiet and keeping the B+ lines quiet. So these here will be replaced with a capacitor that looks something like, I'll just grab one here. They're much smaller. The 4700 version is even smaller than this. So it'll be replaced with something that like this right here. It's a 0.01. I'll replace it with these. I have lots and lots of 4700 picofarad poly caps that look just like this, and I could replace them, but why? I can up the value and just make the filtering all that much better on the screen and on the B+ lines. So these will, replace all of these caps that you see in here that are acting as bypass caps. And in the end, once I have all of these removed, which will be in the next episode, we'll test all of these and see how many of these are actually noisy now that I've desoldered them. We put the super probe on all of these in the last one, and they seem to be relatively quiet, but any type of movement and desoldering these and moving the leads around is definitely bound to make those things noisy, very, very noisy. So there you go. Bypass capacitors, not a big deal. Poly, even a ceramic style capacitor, ceramic disc capacitor will be fine in this circuit. Very, very lenient, I guess you could say. But when it comes to the oscillator circuit, anything that has to do with dial tracking, you want to stay completely away from those. So much to the fact that a lot of the times they hand pick these. So the value on the capacitor might be something, but somebody down the line might be looking for a value that's within a picofarad or two of a certain design that, and they'll hand pick those and use those only for these. This here radio was a special order, and I've learned that since the last episode. There are some components in here that are completely different than the schematic, and I have other radios to compare to, and the other radios are all follow the schematic exactly. So this has some special order components in it, and I'll also talk about that in the next episode and why they put those special order components in. And again, those are in these boxes right here. So this receiver was obviously used in some pretty special purpose. Whenever dealing with RF circuits or any type of a circuit where a non-inductive resistor is needed, you're going to find carbon composition resistors. And you're probably saying, well, these things are really old. Well, some modern test equipment today, alignment equipment, have carbon composition resistors in them right down on the circuit boards, and they're there for a reason. I see people replacing those carbon composition resistors with metal film, and I see them replacing them with carbon film resistors and things like that, and that's an absolute no-no. Again, I'll get into that in the future as well. The engineers have put carbon composition resistors in modern equipment for a specific reason, and if they are bad or out of tolerance, many times, not all the time, but many times they need to be replaced with an exact carbon composition resistor again. Now, in the days of these old receivers, carbon composition resistors were almost all there really were at the time, and they are very, very good resistors. Now, these resistors here are across a coil. So we have this basically to DC. If we use a DC resistance across here, so just a standard DMM to measure this, we're only going to see an ohm or two across this. Now, if you were to replace this particular resistor with, say, a resistor that looks like this, all right, so of course the value would have to match, but if you were to replace this resistor with something like this, you would have all sorts of problems. Why? Well, inside here is a coil. This is a very, very inductive type of resistor. Now, of course, inductive, I guess you could use that term loosely because, it really depends on the type of frequency that is applied to it. But when you have multiple turns of nichrome wire inside of a resistor and you put that across something like this, which is multiple turns of just standard wire, you're going to create lots of problems. So you definitely would want to keep this as non-inductive as possible, this resistor. Unless you really want to start experimenting with the design at hand, then of course you can, fool around, but you would be looking at the circuit with a spectrum analyzer and all sorts of things. So why create all of that extra grief? Keep this as a carbon composition resistor. Now, if you're dealing with an actual resistor that comes from the B+ supply and say goes to the screen, that's not so important. You could use a standard metal film resistor there, or you could use if you'd like, a carbon film style resistor or metal oxide resistor down here. That is not a big deal. But whenever you're dealing with an actual path in a coil circuit, so again, to DC, right across this, if you were to measure this, it would most likely look just like very close to a dead short here. In fact, let's just measure it right now and find out. So I guess it's going right across a coil. So I'll just move this back out here. Hopefully you can see the meter. I'll turn this back on. And we'll take a, so this is DC resistance, okay? So we're not taking an AC resistance measurement or an impedance measurement, in other words. We're taking a, I'll just shut this light off up here and move this so that we can get some more light on the meter and stuff like that. So let's go here and let's just see. So we'll go over here, enter. Okay, so we'll go ohms and we'll just measure across this. So this resistor here is 5.6K. So we have green, blue, and red, and then a gold band here, which is 5% tolerance. Okay, so you would read across this and we're going to see, look at that, 0.3 of an ohm. All right, so you know, to a DC resistance reading, which is this meter right here, you know, it's, or even a DC, if you were to put DC on that coil, that's what it would look like. It would look, you know, it would look like a, get a good connection here, a 0.2 ohm resistor or something like that, right? Another little trick that will fool a lot of people is they'll think that, oh, the resistor is shorted. Resistors almost never short. In fact, I would say 99.9% of the time they don't short, they open, or the value will go high. Many times, if you overheat a carbon composition resistor, the value will go down, but you will see physical burning on the body. So if you were to overheat this to where the color bands had changed and you know, there was a nice big hot spot in the center of the body, this has the tendency to move down a lot. That might move down into the hundreds of ohms. And that was a real problem in some transmitting equipment way back when, some amateur transmitting equipment, i.e. the Johnson Viking Valiant and the Ranger, in that entire series. They put a carbon composition resistor that was a little bit, I guess you could say, underrated on a shunt type regulator, much like the 0D3 regulator here. It was an OA2. And it would overheat that resistor, and throughout time it would get hot and the resistance went down and down and down and down and down. And as it was going down, the tube, of course, was getting more current. So the tube was getting hotter and hotter and hotter, and it would actually melt the glass on the 0A2 tube, and to the point to where it would burn up in the VFO case and cause problems in there. So in an extreme condition where these would have a burnt body and you would see that, yeah, they'll go down, but very, very rarely when they look like this, you know, 99.9% of the time, they'll go high in value, not low. I'm sure if I was to snip this lead open, this resistor will probably be right on 5.6K ohms, and very close with this one too. Again, 5%, no problems. Resistors like this that are in circuit, that are, you know, these are feeding the screen grids down there. These 47K ohm resistors are feeding the screens. Those are most likely going to be a little bit high. I would have to test them to see that though. Again, in RF circuitry, stay as close to the original design as possible. The next step for this, I would say, would be, if you would like to stay close, would be a carbon film style resistor. And then after that, you would move to metal film, metal oxide, things like that. So if you have the chance and you have to replace a resistor across a coil like this, something where you see a dead short like that, you want to stay with a carbon composition style resistor. If you work on older military style radio receivers, many different makes and models will use bathtub style capacitors, and so will higher end power supplies and test equipment. You'll find these things all over the place. Now this is an oil filled design, so they have seals around the lead out connections right here. So these are seals, and what they do is they solder the bottom on, and the bottom has a hole in it. Once the whole thing is put together, they fill it with oil, and then they put a little patch of solder across that hole where they've filled it up, and that seals it up and keeps the oil inside. Now over time, these things fail and they leak miserably. I've opened up AR88s and CR88s and all this particular type of radio receiver with these bathtubs in them, and I've seen huge puddles on the bottom of the case where these things have been dripping over time. Now, a lot of people, a lot of the techs seem to think that these things are absolutely fine and you can keep them in circuit and, you know, keep using them if they're not leaking. No, you can't. These things are electrically leaking by now, and if they're not leaking physically, any type of soldering or any type of tampering and even temperature change now, because these things are so old, will affect the seals, and eventually they'll start leaking their not so friendly oil out of them. And you just don't want these things in circuit anymore. I see, again, a lot of audio guys using these things in audio amplifier service. They collect them and they think that they make their audio amplifiers sound better because they're using these older components. Yikes. So these things are past their expiry date and they all have to go. Now, depending on how courageous you are, a lot of people, what they do is they open these things up. Basically, they peel the bottom pan open on this thing and they, take the guts out of these things with, that not so friendly oil. And what they do is they put these capacitors inside these cases just to hide them. Now, that's up to you if you want to do that. I really don't want to bother with these blocks. Reason being is if one of these things ever need to be replaced, it's very easy just to desolder this and replace it. Why would I want to make it so that I have to pull out this entire block and fish around in here for some capacitors and pull them out of here and do all that kind of stuff all over again? Now, mind you, I expect these capacitors to last the remainder of the life of this radio receiver. And it's the same with these capacitors here. I imagine by the time this radio receiver is done, these capacitors will probably still be working. All right. So again, I don't expect these things to ever be changed again. They're very, very dependable caps. And I put actually quite a bit of time into testing these things. I talked a bit about that up on Patreon as well. So anyways, these capacitors here can be replaced with a standard poly style capacitor or even a disc capacitor of the same value, all right, and the same voltage rating and things like that. So again, these are mostly basically used for bypass and a decoupling service in these radio receivers. All right. Sometimes you'll come across a larger bathtub style oil-filled capacitor that will be used as a filter in a B+ section. They had some very large versions of these things that they used for filtering, basically the supply for the CRT and some oscilloscopes, things like that. So you'll find bathtub capacitors of all makes and sizes and filled with all sorts of wonderful things called pyranol and that kind of stuff as well. So again, I just like to get rid of these things and clean the chassis out and just not deal with them at all. Again, the application of the capacitor, it's not in a timing circuit and it's not in an oscillator circuit. They're just used as decoupling and bypass. So you can use a ceramic capacitor or a poly style capacitor, and even if you had a low enough value, in many cases you could even get away, depending on the application, you could even get away with a low value electrolytic if you needed, not that incredibly specific. If you enjoyed this video, or you're just enjoying my videos in general, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the near future. We'll be looking at solid state equipment and vacuum tube equipment alike. So there'll be a lot of repairs and restorations, troubleshooting, and circuitry design on this channel. So if you're all about electronics, like I'm all about electronics, this is the place you want to be. Don't forget to subscribe and tap that bell symbol. That way you'll be notified as soon as I post a brand new video. I have an ongoing electronics course on Patreon with a lot of extended electronics information. I also share many of my personal electronic inventions and designs there. Many of these inventions and designs you've seen me use on this channel a lot. A lot of really great troubleshooting tools to make your life all that much easier. You're definitely going to want to check that out as well. I'll put the link just below the video's description under the Show More tab, and I'll pin the link at the top of the comments section. So if you click on the link, it'll take you right there. All right, until next time, take care. Bye for now.